Hey, good morning, everyone. Almost 9 o'clock here, so we'll wait a few more minutes. How did this ratio test go on this series? Anyone have any issues with that? Were you all able to determine what this does, whether or not it converges or not?
Yeah, I was able to do the convergence part.
Okay.
But I just had one question real quick.
Yeah.
You have n+1 factorial, and you take it apart to n times n+1. I mean n factorial times n+1, right? You could do that. Can you do that with the n+2 as well? N+2 factorial. Are you able to do that?
Yeah. So we can turn n+1 factorial into n+1 times n factorial, right? So if you have, I'm guessing what you're asking is when you plug in n+1, right, for n, then it becomes n+2 factorial. That can turn into n+2 times n+1 factorial.
Oh, okay.
Right?
Yeah.
And just think about it this way. I mean, it's because this is really n+2 times n+1 times n -1 times n -2 all the way down to 1, right? So if you group all these together, that's n+1 factorial, and then you have this up front. And it would go the same way with like n+3 factorial, right? n+3 factorial could turn into n+3 times n+2 factorial. Okay, well, it's 9 o'clock. Again, I apologize that we're here again on Zoom, but I really feel like this will be it. Next week, I should be good no matter what. So yeah, let's get down to business. We have, again, a lot to do today. We are going to pick up where we left off. We were talking about power series last time, and specifically that we have this new idea that we're going to take a series, excuse me, and we're going to add to it this new x to the n within the series. And since x is a variable, we can now look at this as being a function of x. And so what we need to make sure is that we can figure out what x values we would plug into this that would guarantee convergence, right? We would need to have convergence for this to be defined. That's very important, all right? We know that not all series converge. So the value of x will basically dictate whether or not this series converges or not. For some values of x, it will converge. For some values of x, it won't. And it might be that x is completely irrelevant. It could be that it doesn't matter what x we plug in, it will converge, or it doesn't matter what x we plug in, it will always diverge. So it goes back again to this concept I was trying to illustrate last time, that if you have a function, oops, wrong color. If you have a function, something we've studied in the past, like, f of x equals, I don't know, x plus 1 over x, this function is not defined for all values of x. It's defined for everything other than 0, right? Can't plug 0 into this. So as long as you plug in some number other than 0, then we can find a value. The same idea here. We're trying to figure out what x values we plug in, that when we plug them in, we actually get a value, which would be whatever the series converges to. If we plug in an x where we get divergence, then it's the same thing as trying to plug 0 into that. It's not defined, it diverges, okay? We don't get a numerical answer. So this will all hopefully start to come to light here as we proceed. So let's get to our first example, very important example. It's going to come up several times. It's going to be your first example of a power series. All right. So here it is. So when you have a power series, this C sub n, I told you, the C sub n right here is just going to be a formula that creates the coefficients, right? It creates all these coefficients. So that C sub n is exactly what the A sub n used to be for us in the previous sections. It was the formula that creates the numbers. Now we call it C sub n here, and there's a reason we call it C sub n, but we'll get to that later. But this C sub n can be any formula, right? Anything we want. So our first example, we're going to take the easiest formula we could possibly have for C sub n, and that is C sub n is the constant 1, which means that every coefficient is 1. So if I take that, take this general formula, replace C sub n with the constant function 1, and then start plugging in values of n for the powers on the x. Of course, when I plug in 0, we get x to the 0 times 1, which is 1. Then we replace the n with 1, and we get 1 times x, and then 1 times x squared, 1 times x cubed, and we're adding all those up forever, right? Well, if we remove, we don't have to write the ones, right? We don't need to actually write these, so we'll just write it as 1 plus x squared plus x cubed plus x to the 4th forever and ever and ever, right? So that's our first example. So what we would like to know is, what is the domain of this function? For what values of x does this thing converge? And you might initially look at that and be like, well, it's always going to diverge, because if I plug in a number, then I'm just adding up all these numbers forever, right? But that's not the case, all right? What you have to do is, and this is where students sometimes have trouble with this, think back to when we defined our geometric series. Y'all remember the formula, right? For geometric series, this was it right here. If you look at a geometric series, it looks almost exactly like this, right? We have some constant plus some constant in front of r, plus that constant in front of r squared, and then the constant in front of r cubed, constant in front of r to the 4th. Do y'all see that this is exactly the same as a geometric series? Well, look at this one right here, right? This right here, that's really like the A was in this formula, right? If that was a 1 and that was a 1 and that was a 1, and then instead of having r, do y'all see the r's are just like the x's, right? So that first example of a power series that we're looking at here looks exactly like a geometric series, and we know what happens with geometric series, right? Like if we say, hey, the A is 1 and the r is x, right? We replace the r with x. What made a geometric series converge? When did a geometric series converge?
As long as it was less than 1. Right.
When the absolute value of r is less than 1, right? That's exactly what we know about geometric series. It'll converge when the absolute value of r is less than 1. Well, since the series up here is exactly the same as this series, we just replace the a with 1 and the r with x. Then in our case, right, this thing should converge so long as the absolute value of x is less than 1. Any questions on that? I mean, it's exactly a geometric series. Now, with geometric series, though, that we looked at in the past, wasn't r a number? Wasn't r like a fixed number? It'd be like, maybe r is 1/2, or maybe r was, 2/3 or whatever. And so the r never changed in the previous section. The r was fixed. Here we're saying the r is a variable. And so what values of that variable can you have and still have convergence? And so we're saying, look, as long as the absolute value of the x is less than 1, we should have a convergent series. We should have a well-defined function. Okay, so questions? Main thing you need to understand here is the connection that this looks like a geometric series. Is that all right?
Real quick, when you said up there, C sub n is basically our A sub n. So is that basically saying that C sub n is our sequence?
It is. Yeah, A sub n is a sequence, exactly. Now that's a very, very generic sequence. It's just the sequence 1, 1, 1, 1, 1,
Yeah.
1, 1, 1. So obviously they're going to get more complicated.
Yeah.
But this is the first example. And when we let C sub n be 1, then we get this thing that looks like a geometric series. And then we actually know when it converges and when it doesn't, which is nice. This is our first example. So we want it to be something nice, something we recognize.
Yeah, so we can get the idea.
Yeah. Okay, so therefore, right? Therefore, the domain of this function, now that function is the one up here, right? Come on. That's this one right here. right? With C sub n being 1. The domain of that is all the values of x that are between -1 and 1. So look, everyone, this is where you have to have like the big aha moment, I guess. What I'm telling you is that we have a function that is defined to be an infinite series of powers of x, right? This is a series of powers of x. It is a power series, but it is a function and it is defined as long as we're looking between -1 and 1, which means we should be able to graph it, right? If it's a function, we should be able to graph it. I should be able to plug in a value for x and see the picture. So let's take a look at the actual picture. So what I want you to do, oh, I forgot to point something out. When it converges, right? Think back to geometric series again. When we pick a value between -1 and 1, we should get convergence to this. Now I know that's hard to read. 1 over 1 minus x. That's coming from that formula a over 1 minus r. Remember from geometric series, all geometric series converge. When they converge, right, they converge to a over 1 minus r. And if for us, the a is a 1, right? And the r is an x. So this power series, right? This power series, so long as our absolute value of x is less than 1, that series right here should converge to this value, to that function. So geometrically, here's what we're saying. What I've done here is I have graphed, what you're seeing in red is the graph of 1 over 1 minus x, okay? That's the graph of 1 over 1 minus x. And it goes up and it comes down over here, keeps going. And then over here, there's something else going on this side. The black, you see this black is the graph of the power series. And right now, so the power series is this, right? That's the power series. Right now, I'm just graphing the first term. Do y'all see that 1 right there? So if you graph the 1 function, it's just a flat line. Now I'm going to add another term to it, 1 plus x. So now I'm getting the first 2 terms right there. Can you all see that? 1 plus x. I'm graphing that. That looks better. Let me do another one. 1 plus x squared looks like this. Let me add another one. Boom. Let me add another one. Watch what's happening to the black one. Now these dotted ones, I'm leaving behind the previous graphs. Okay, do y'all understand that? So you can kind of see what's happening as it's transforming. The more terms I add, watch how the black one starts to map, like march its way towards the red one. Do you see how it's converging towards the red one? But it's only converging towards the red one in this little window, in this white window between -1 and 1. Once you go outside of -1, do you see that our black curve, all these dotted ones just kind of go off? They do not match up with the red one. That's because this is only valid between -1 and 1. These two things should only be valid or match up with each other between -1 and 1. Once you go past that, all bets are off. All right? I'm going to keep going a little bit more. It gets closer, 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 closer. And the thing is, it goes forever, doesn't it? I can't go forever on the computer, but if you continue to go out, the black one is going to line up. It's going to start to land right on top of the red one. It's going to get closer and closer and closer and closer. But again, the important thing is only in this little window, right? Only in that little window is it matching. Outside that window, it's not matching. And so you might be like, well, that's not very helpful. We have to stay in this little window. Later on, you'll see what we'll be able to do is we'll be able to just shift it left and right. So if we want to know, if we want to approximate this red function over here, we will just move the series over and it'll match up over there. Don't worry about that now. Okay. So that is the idea. The idea is that we can take this function 1 over 1 minus x and we can match it with a power series within a certain window, and then essentially they're the same two functions. All right. One of the things students will ask me or say is like, why would why would I want to deal with this nasty, big old long thing when I've got this really, really nice formula right here, right? Like I have the function, like why all that crap, right? It's like, it seems like we're complicating something for no reason. Well, the reason why we need this is because this is a very simple function. But what about a complicated function? What about a really complicated function? Like, I don't know, think about the most complicated thing you can come up with, you know, like the square root of sine something, you know, over, you know, tangent with logs in it, exponentials, something really complicated where we don't have a simple formula for it. And think about if you were asked to integrate that or differentiate that. Like, so if I give you a really complicated function right now, can you integrate it? We've learned that in this class, if integration is hard, but I even told you that, like, if you look at the world of all functions, the chances that you're going to be able to grab a function and integrate it by hand is essentially zero. So our ultimate goal here is that if I give you a very complicated function, can you convert it to its power series? Because if you can convert it to the power series, imagine me asking you to integrate that. If I asked you to integrate this, would that be easy for you to do? Well, term by term, right? One by one. And they're each powers of x. And we all know the power rule. It's super simple, right? So you should be able to integrate this without any trouble. A more complicated function you might not be able to do. But if you can convert it into powers of x, you're in business. And that's what we want to be able to do. And that's what computers do, right? They take a function, they convert it to its power series, and then they integrate or differentiate. So that's kind of, we're trying to see the forest through the trees here. Ultimate goal is to be able to take an arbitrary function, convert it to its power series, and then you can do whatever you want with it. Integrate it, differentiate it, do whatever, okay? So that's our first example. Let's move on. Now we need to talk about the general definition. So right now, what I've given you is a power series, right? I gave you the general idea of power series, but we're going to generalize it even more. So this is a definition, a power series about A, okay? A power series about A, that's the way you'd say that. Or you could say a power series centered at A. Or you could say a power series in x minus A. Now that last one, I don't see that very often. That last one, I usually see the first two in different textbooks. And moving on in like other classes, you'll usually see the power series about A or the power series centered at A. All it is the same formula we had before. Okay, let me go back to this formula for a power series. Here's the formula we had before. The only difference is instead of having x to the n, we are going to replace the x with x minus a. Now, think about how that impacts functions back when you were learning about functions, right? Back in college algebra. If you take a function, let's say you know what this looks like, you graph it, whatever. What does doing something like subtracting 2 on the inside of the function do to that function? It's a transformation. You remember what it does? If you subtract 2 inside the function. What if I subtract 2 outside the function? What would it do to this graph?
It'll shift it to the left.
This right here, okay, so this right here would shift it down 2. It would take that entire picture, move it down 2. If you subtract 2 within the function, it actually does the opposite of what you think. So minus 2 makes you think left 2, but when you're doing left and right shifts, it's opposite of what you think. So this actually would move it to the right 2. Right, so anytime you subtract a number inside of a function, it moves it left and right. So by replacing the x with x minus a, what this allows us to do is shift left and right, which is exactly what I was telling you about when I was showing you this picture. It's like, okay, it's only valid here, but what if we want to talk about it up over here? Well, we're just going to shift it. We're just going to move it over. So that's what the general definition is. It's the same thing, replacing the x with x minus a. And then you get the same sort of idea here. You have all these constants that are sitting in front, right? All these constants. And then instead of x to the n, it's, you know, x minus a to all these powers. Okay, understand that's the general definition of a power series. Centered at A, or a power series about A. Now there's three things, right? Three things that I want you to notice, right? The previous series that I gave you, the first form that I showed you up here, you know what? This is a typo. Sorry. This should say A equals 0. So go back up to the formula that I started with. If you look at this, this was actually x minus 0 to the n. Do y'all agree that's the same as x to the n? So the a here, when I gave you this, the a was actually 0. And when a is 0, you just get x to the n. All right, that's the first thing I want you to notice about this. The next thing, make sure you understand, is that this term right here, sorry, this one right there without the c, this right here to the 0, of course, is 1, right? So that's why this right here is just c sub 0. Also, okay, also notice this. If x equals a, right? If x equals a, what do all of these do? If I tell you right now to take this power series and replace x right there with a, wouldn't you get zeros everywhere? You know there? If I tell you to look at this right here and replace all the x's with a's, wouldn't it zero everything out? Wouldn't you get, then wouldn't it converge? Right? It would converge, right? Because you're adding up a bunch of zeros. So that converges. So if x equals a, then these are 0. Thus, if x equals a, the series converges. That means every series, every power series out there, every single one of them will converge if x equals a. If x equals a, every power series will converge at x equals a. So back in our example right here, this one that looked like a geometric, just think about it. What did I say a was here for that? What's a for this power series?
0.
0. So if I plug in 0 for x, I'm going to, of course, have 0 plus 0 plus 0 plus 0. It's going to be 0. I mean, it's going to converge. So that's what this is saying. And that's an important aspect of all power series, is that you're guaranteed convergence at least at one point. Okay, you'll always get convergence at least one point, and that's when x is a. All right, let's do some examples, because this is, I know this is a lot to kind of wrap your head around. Let's look at this right here. If f of x is this power series, right? This is a new power series. I want us to answer these questions. So let me take this to our notes here. And first of all, what is a? So what is a here?
N factorial?
I'm sorry?
Is it n factorial?
No, no. So we have the general formula here looks like this. That's what a general power series centered at A looks like. So maybe it'll help if we identify the C sub n. So C sub n is the part that creates the coefficients. Do y'all see that n factorials are C sub n? And then we have x minus a number to the nth power. Well, that right there is the x minus n. This is, x minus a. This is x minus something to the n power. What has to be there?
0.
0. Yeah, 0. So 0. So A is 0. If you ever just see x to the n, then A is 0, all right? Understand? Here A is 0, and C sub n is the n factorial. Now, find the domain of this function. This is the big step. We need to figure out when this thing converges and when it diverges. Now, in the previous example, we were able to look at it and say, oh, that looks like a geometric series. We know what it does, right? This is not a geometric series. It's not. So, because the n factorial out front. So I need to figure out what test should I do from the previous sections to try and determine the convergence or divergence of this. And with all power series, we're going to use one test. Guess what test?
Ratio.
The ratio. The ratio, the almighty ratio test. That's why I call it the almighty ratio test. It's what we use for power series. So I'm going to use the ratio test here. Now, when we do the ratio test, what we need, remember, is we need to do this limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And what we want for convergence is for that to be less than 1, right? If this limit is less than 1, we've got convergence. If it's bigger than 1, we have divergence. And if it equals 1, we don't know anything, right? So I've got to run the ratio test on this entire thing, okay? On the entire thing. So here we go. Limit n goes to infinity of, okay, first I'm going to plug in n plus 1. So it becomes n plus 1 factorial, and then x to the n plus 1. Not too bad. Over, just replace n with n, so n factorial x to the n. Now I'm going to clean up the numerator. I'm going to write that as n plus 1 times n factorial, then x to the n times x over n factorial times x to the n. So I'm just using properties of the, splitting up that factorial, and then I'm taking the x to the n plus 1, splitting it off. And y'all see we get some nice cancellation, right? Gone, 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 gone. And so what we're looking at here at the end is this: the limit as n goes to infinity of n plus 1 times x, right? That's all we have. Do you understand? I want to know, right? You want to know, we want to know, for what values of x, right? What values of x would make this thing stay smaller than 1, right? We want to know what makes that less, what values of x makes this true. So look at what's happening here. When you let n go to infinity, where does this thing go? Infinity, right? The n plus 1 is getting huge. So this thing is trying to get like massively big, right? And you're trying to control it and keep it less than 1. The only thing you have control over is x. That's all you can control. So how are you ever going to overcome this infinity? Is there any way to overcome this infinity with you controlling x? 0. That's it. You can let x be 0. If you let x, I'm not saying let x approach 0. I'm saying let x be 0. If x is 0, this left side, this is all 0 because this number is getting bigger, but this number is 0. Don't confuse this with Cal 1 where we had this form 0 times infinity. and we had to do like a thing where we take one and drop it down. Remember that from Cal 1? Not the case, because this was if this was approaching 0, approaching infinity, then you had a problem. Here, what we're saying is I control x. If I let x be 0, this will be true. What if I let x be any other number? If I try any other number, doesn't matter what it is, right? Give me, even if it's like 0.000000000 with a million zeros, then 1 at the end. This number will overtake it at some point and it'll become infinite. So the only way to control this and make this happen is if I let x be 0. And that is it. Then we will have convergence, right? If x is 0, we have convergence. Otherwise, this thing diverges. So what is the domain of this function? The domain of this function is what? What's the only value of x I can have to make this thing converge? 0, right? That's the only, it's not even an interval, it's a single point. So how do we write that? We write a brace, and then we put 0, and then we put another brace. That's how we represent a single number as a set. Now look, this is weird, okay? Because the first example I'm giving you here, what you're seeing is that we have this series. We're saying this series is a function as long as we can find a value of x where this doesn't, where this converges. And we were able to find one value of x and one value of x only where it converged, and that was x equals 0. And when you plug 0 in here, you get 0 because you're adding up 0 infinitely many times. So this is like a very boring function. If you were to look at it, here's what it would look like. You can only plug in 0, right? You can only plug in 0. And when you plug in 0, you only get 0. That's it. That's your function. A single point at the origin. And that's a useless function. The idea here, the bigger idea is for you to understand that for this particular power series, the only value of x that makes any sense to keep this thing convergent is a single answer. All right? It's a single answer. Now, I think I have a picture of what's going on here. And that was not supposed to be like that. So here's the power series. What I'm going to do is I'm going to have the computer start adding up values. And what you'll see is as I add these things together. So what I'm doing is I'm taking 1 plus x plus 2x squared plus 6x cubed. That's basically this formula right here. And we're adding these up forever and ever and ever. And the computer is adding them. And right now our x value is a 1. So I'm putting a 1 in here for the x. And you can see that this sum is starting to become infinitely large. And it goes off, it gets huge. It's not converging. And if I change the value of x, this sum, again, takes off to infinity. See 10 to the 12th? This is a huge number. The only way I can control this sum is if I change my x value to 0. And if I change the x value to 0, then don't worry about the red. That's because the code I have in here didn't know how to handle that. But basically, if I let x be 0, then it's going to converge because we're going to have a bunch of terms that are all zeros added up. So we get convergence. Only at one point. The picture of this is a little bit weird. If I start graphing these like this, what you'll see is that if I'm at 0, this thing stays there. But if I move to the left or right, this function starts to get crazy big. And it's not headed towards anything. It's headed towards 0. It's smashing, everything's smashing into just basically a single vertical line through the y-axis. And so, yeah. So look, if you're still unsure about what the hell we're doing right now, let me do 2 more examples. As I do the next 2, hopefully this will start to come to light what's going on here. So let's look at our second example. I want us to do the same exact thing for this one. So it might help you, if you look at this one, it might help you to look at it like this, 1 over n times x minus 3 to the n. Hold on, we can't, I messed up. We have to start this sum at 1. Sorry, we can't start it at 0. Let me go fix that in the notes. Now I changed it to a 1, so you might be like, oh, wait a minute, it's not a power series anymore. Power series have to start at 0. Remember we said that you can always remove, add, or take away a finite number of terms and it doesn't change the convergence or divergence of a series. So that's still in play. I just can't have 0 there because I have division by 0. So when you look at this, what's A? Is it obvious? Yeah, hello?
3.
3, A is 3, okay. Again, we're going off of that formula here. So the A is the thing that's being subtracted from the X. So we actually have that happening now, right? We have X minus A to the N. So we've got A is 3. And then C sub N is the formula that creates the sequence of numbers. And that should be what?
1 over n.
1 over n. Okay, good. Now, let's find the domain. So to find the domain, I need to run the ratio test. And so I'm going to take the limit as n goes to infinity. And now I'm going to use this version right here. That's the version I'm going to put into the ratio test. So I have x minus 3 to the n plus 1 over n plus 1 over x minus 3 to the n over n. Then I'm going to flip it, do my algebra here. Let's see, on top, I get x minus 3 to the n times x minus 3 over n plus 1, and then times n over x minus 3 to the n. Y'all understand that algebra? What I'm doing there? If you did the homework for ratio test, you had to do this a bunch. So, I mean, you just kind of get used to this idea of flipping things over and splitting this up. We get cancellation here, and that's the only cancellation we get right there. So watch what I'm going to write next. The way that I like to do this, and I recommend you do the same thing, is in the new absolute value, what I'm going to do is I'm going to put everything that has n's together. So in the front here, I'm going to put n over n plus 1. That's basically taking that, putting it over that. And then I'm going to say times, and then I'm going to put the x minus 3 next to it. Now, just like before, I want to know what's going to keep this less than 1, right? What values of x will keep that less than 1? If I can keep it less than 1, then I should have what? Convergence? Well, what happens when n goes to infinity?
Infinity over infinity.
Does it do what the previous problem did? The previous problem, when we let n go to infinity, this went to infinity, right? So the only way to control that was to let x be 0, right? But here, what happens when n goes to infinity? What does that head to?
Towards 0.
Infinity
You
over
get, if n goes to infinity, you get infinity over infinity, don't you?
Mm-hmm.
So you can do L'Hopital. If you do L'Hopital, you'll get what?
1 over 1, so 1.
1 over 1. So just 1, right?
Mm-hmm.
So when you take this limit, this piece here actually goes to 1, right? Which that's not blowing up, right? You don't need to control it. It's headed to 1. So let's just go to the next line. We've run the limit. Okay, the limit's gone because we're going to let that go to 1. And what we have is the absolute value of x minus 3 is all that's left there. And then we need that to be less than 1. Agreed?
Agreed.
Okay. Now, I'm going to take a little sidestep here. I just want to remind you. When you say the absolute value of x is less than, let's say, 4. Let's say I were to try and ask you to solve this. Tell me about the x's. The way you solve an absolute value inequality is you drop the absolute value. Okay, you get rid of the absolute value, and you put just less than this side. And then on the other side, you put this greater than the opposite of that 4. So to say the absolute value of x is less than 4 is the same as saying x must be between -4 and +4. So if I look at this and I do the same thing, this is telling me that x minus 3 must be less than 1, but greater than what?
-1.
-1. Okay. And now what I'm going to do is I'm going to add 3 everywhere. And when I do that, I should get 2 less than x less than 4. Are y'all okay? So let's just make sure we understand what we have actually done here. We were given this function f of x equals this power series. And we were asked to find the domain of this. So to figure out what values of x do you have to plug into this to get convergence so that the function is defined. And so what we've determined so far is that if we run the ratio test, as long as we keep this limit below 1, we will have convergence. And so we've figured out what the x would have to be to keep it less than 1, right? Agreed? Yeah. So far, this is our domain. So far, we are not done. Okay, we're not done. And this is where things get a little tricky. That keeps it less than 1. What about if it was equal to 1 though? Like, what if this was equal to 1, right? What if this was equal? What if this was equal? What if this was equal? What if that was equal? I don't want them to be equal, but think about what would happen if it was equal. What would the ratio test tell us?
It diverges?
No, that's if it's bigger than 1. If it's bigger than 1. So if it was bigger than 1, we know we have divergence. If it's less than 1, we know we have convergence. But what if it's equal to 1?
Inconclusive?
Inconclusive. The test fails, okay? That means we still don't know what happens when it's equal to 1. We don't know. It could converge, it could diverge. And so right now we know for sure we have convergence here. For sure we have convergence. What we don't know is this. If x equals 2, we don't know what it does. And we also don't know if x equals 4, what it does. Do y'all understand what I'm saying? At the 2 endpoints of that interval, if you plug 2 in for x, right? Just try it. If we plug in 2 for x, right here, we would get equals 1, not less than 1. So we need to figure out what happens here and what happens here. We must check the endpoints. Okay, we must check them. Now, what do I mean by check them? I mean, take the original series, okay, which was right here. Take the original function. I'm going to copy it here. I'm going to put it down here just so I can write it. So we need to take the original function, and I need to see what would happen if x was 2. All right? If x was 2, what would happen? So I'm gonna do it. So if x is 2, it becomes sum n equals 1 to infinity, and change that 0 to 1. N equals 1 to infinity of, now I'm replacing the x with 2. So 2 minus 3 to the n over n, right? And that becomes sum n equals 1 to infinity of -1 to the n over n. Isn't that what happens if I replace the x with 2? Somebody tell me what that does.
It's an alternating.
It's alternating series, right? And so couldn't you run an alternating series test on it? And you would figure out, I'm not going to do it, but you could show now, you would do an alternating series test and you would show that it actually converges. You would have to show that though. All right. I'm not going to show it because we don't have time. Understand? So that means when we let X be 2, we do get convergence, right? So we want to include that in our answer. What we don't know yet is what happens at 4. So now we're going to do the same function and we're going to replace X with 4. And when you plug 4 in there, you get 4 minus 3 to the n over n. But that equals 1 to the n, right? 1 to the n over n. But that's just 1 over n, right? And what does that do?
Diverges.
Diverges. Why?
It's a harmonic series.
Harmonic, exactly. Or you could say it's a P series with P being 1, but I'm going to say it's harmonic and it diverges, which means we don't want that, right? We don't want that as part of our answer. So we try and plug 4 in, it's going to diverge. We plug in 2, it will converge. So now we're ready to write the answer. Okay, the answer for the domain is this. The domain of this function is this interval, 2 to 4, with a bracket on the 2 and a parenthesis on the 4. If you'd like, you could write it this way also. X greater than or equal to 2, strictly less than 4. Either way. These are some of my favorite problems to give on finals because you have to run a ratio test, you have to run a limit, right? And you have to check the endpoints, which means you have to be able to do 2 types of series. One of them, they may both converge, they may, both diverge. It just, one may converge, the other might diverge, but you're going to have to run 2 tests to do that. So it's like one problem encompasses all these ideas, right? I love these problems, all right? I love them as a gauge of what you know. We good? So in the previous problem, we saw that the only way that this function could converge was at a single point, right? A single point. And then on the second problem, what we saw is that the only way that this function converges or this series converges is if we let the X be within an interval. So first example was a single point. This answer, we're getting an interval. Let's look at it visually. What's going on with this series? So right now, the value that I have for X is 2.6. So if I plug 2.6 in here, should I get convergence or divergence? 2.6. What did we say? It would converge if we were between what and what?
2
and 4, right? So this number, 2.6, is between 2 and 4. I'm going to start having the computer add up all these pieces. It's going to replace X with 2.6. Watch what happens to this last number. Does it converge or diverge? Watch it. Oh, hold on. My wife just set the alarm off in the house. Okay, I think she's got it. All right, so do y'all see this number, 0.333? Do you see that it's converging? It's staying around 0.33, negative 0.33, right? Now, what will happen if I change my value of X to 3.3? See, I still have a nice number. I can keep going out. It's converged. But if I go outside of 4, right? Well, let me try and get to 4. I don't know if I'll be able to get to 4. There, 4.3. So now if I start going out, this number is going to start blowing up. You see it blow up? This number's, it's not going very fast, but it is getting bigger. It's not, you don't have that same convergence. So here's a picture of it visually. If I start drawing this, start drawing all the graphs, so I'm putting all these pieces of the series together, notice that the black curve is headed to something. within this window, within this little window, it's headed towards something. And that window is between 2 and 4. If you go outside that window, it starts going crazy. I said, let me do 3 examples, then we'll talk. Let's look at the last one. Hey, isn't that your, oh, that was, oops, sorry. That's not the one I gave you to do on your own, right? We did this in class, didn't we? Kind of. It's different though. We did something like this, but we didn't do this exactly. What we did, look, what we did in class last time is I had you do, or was it? It was this one, right? Yeah. I had you do, we did this in class. So it's not exactly the same. Let's do it. Same questions. Whoa, that is complicated looking, isn't it? Isn't this a really complicated looking thing here? So I would recommend you look at it like this. -1 to the n over 2 to the 2n times n factorial squared times x to the 2n. What I've done is I've separated, oh, and n starting at 0 here. What I've done is I've separated the part that's the c sub n away from this piece, the part with the x. Let's just go straight to the ratio test. Let's try and figure out the domain of this. This is called the Bessel function. Okay, I'll talk to you a little bit about what the Bessel function is in a minute, but let's actually make sure it converges or see where it converges or diverges. So I'm gonna run the ratio. All right, here I go with the ratio. Limit x goes to infinity. All right. We have -1 to the n plus 1 over, and I'm going to put the x to the 2 times n plus 1 up there with it. And then over 2 to the 2 times n plus 1. And then we have n plus 1 factorial, but then all of that squared. And then all of that over -1 to the n times x to the 2n over 2 to the 2n times n factorial squared. So if you look back from last class, I'll put that back up in a second. If we look back from last class, we did basically, this thing that we did in class, this was basically the c sub n. I did not put the x part in here. All right, because I wanted you to at least have seen how you deal with this. So I want us to actually go back and look at these notes because I don't want to go through all this work again, how we mess with all these exponents. What did all of this do? At the very end, what did we get here? We got this, right? We got that? Okay, let's just remember that. I'm going to copy it and I'll bring it over. Copy. Just going to paste it here. The thing I need to figure out, okay, everything in yellow is resolved. In other words, we know what all of that does because that's what not that part. Yeah, because we did that in class already last time. What we really need to do is just make sure that we understand what happens to this part. So that becomes x to the 2n plus 2. And this one is x to the 2n. I can rewrite that as x to the 2n times x squared. And so everything cancels. Well, not everything cancels, but we get the x to the 2n's to go away. Y'all understand that? So when we go through all the work for this, ... there's a lot that I'm not showing. What we would get is the limit as n goes to infinity of, now we get the part that has the n stuff in it, which is this. But then we would also have here this one piece that was still there was the x squared would be here. Do y'all understand that? Do I need to go through that anymore? I'm leaving a lot of the detail to you. What do we want that to do? In order to have convergence, what do we need that to do? We need that to be less than 1, right? Let's figure out what values of x we need in order for this to be smaller than 1. Well, wait a minute, hold on. Where is this headed?
0.
0, which means it doesn't matter what x value I plug in. No matter what x value I plug in, this thing's headed to 0. It's gonna basically kill this off and make this less than 1 all the time, which means I can plug in any value of x. And keep in mind, you cannot plug in infinity for x. Infinity is not a number, right? So you can't say, oh, well, what if I plug in infinity? Then we have 0 times infinity. I understand, but you can't plug in infinity. You can plug in a cajillion, that's fine, but it doesn't matter. This is going to get small enough to kill this off. So that means, what does this mean? What does this mean? Doesn't matter what x I plug in, right? Which means the domain of this should be what?
All real numbers.
Real numbers. The domain is negative infinity to infinity. These are the ones we love. These are the types of power series we love, because basically it's a function that has as its domain everything, so it should have a graph. It should actually have a graph, all right? And now I'm going to show you the Bessel function, all right? I'm going to show this to you by going back here to my notes, and I'm going to spoil it first. That is the Bessel function in red, okay? That is the Bessel function. Now, this series creates it, watch. So I start with nothing, and then I start creating a parabola, and then a 4th degree, no, this is a 6th degree polynomial. Sorry, I went too far. Here's a 4th degree polynomial. So what I'm doing is I'm plugging in values of n here, and we're starting to build up the series. And just watch what happens to this thing. It's pretty freaking amazing. You see I'm building out that function? Now that is ugly as hell. I agree that is ugly. Look at those numbers, man. They're massive. But we are creating this function. All right. That is, and if you were to go forever, you get what's called the Bessel function. So this is the first function that you've ever been introduced to in your life that there is no other way to write it. Okay. So like, you know how in the beginning I said, the very first example I had, I said, oh, okay, 1 plus x squared plus x cubed. That looks like geometric. And that really turns into 1 over 1 minus x as long as the absolute value of x is less than 1. I said, oh, all of that really equals this, right? As long as this is true. And I asked you, like, why not just stick with this? Like, that's so much easier than this, right? That's because there's a way to write it, okay? Like, this is a nice, clean way to write that infinite series. There is no clean way to write the Bessel function. There's no clean way to write it. This is what it is. It is defined to be an infinite series. That's the definition of it. Now, you may be going, well, who cares, man? It's, you know, what's the use of the Bessel function? The Bessel function models wave behavior on a, oh, I'm going the wrong way. It models wave behavior on the surface of like a pond. So if you were to have like, imagine you have like a cup, okay? Let's make it a really big cup, and you've got water in there, and you drop something right into the middle, right? Drop a ball right into the middle of the pond. In the center where you drop the ball, you're going to get large waves, right? But as you propagate out to the edge, the waves dissipate down, and they follow this model of the Bessel function. Another way is if you think about a drum. Okay, think about a drum, a drummer, right? So that's a surface that's been pulled taut, and if you hit it in the middle with the drum, it creates a wave. You don't see it with your eyes, but it creates a wave on the surface of that drum. And this is the wave pattern for that. All right, now this is a two-dimensional, well, it's really one-dimensional, but you can extend this to more dimensions so you get the three-dimensional surface and you can figure out the wave patterns. Let me just Google it so you can see it. They've got some pretty good, I should have had some 3D stuff ready to go here, but Bessel function. So the Bessel functions have different orders. I think this one. Yeah, there we go. Something like this. Right. So you can look at like the vibration on a surface and it's modeled with a Bessel function. Now, I'm not going to go any further than that. All I'm trying to do is to convince you that there are functions that are defined to be power series. There's no other definition of that. That's what they are defined to be, and that they are used throughout physics and engineering. They model things in the real world. All right. So that's your first introduction to one. Now we have an important theorem. On the three examples we just did, right? On the three examples we just did, think about what the domains were. On the first example, our domain was a single point, right? On the second example, our answer was an interval. And then our third example, our domain was everything, right? Those three things happened. There's a theorem that says for all power series, doesn't matter, give me any power series, there are only three possible answers for when it converges. Three, that's it. There's only three different things that can happen. It will converge only at a single point when x equals a. It will converge for all x, which was our third example, or it will converge on some interval, meaning that there's some positive number r, which we will have a name for that in a second. There's some positive number r, so that is, as long as the absolute value of x minus a is less than that r, then we have convergence. That's it, three possibilities: single point, interval, everything. You can't have two intervals, all right? This is important. You can't have two intervals that are separated from one another. Can't have that. This theorem says it has to be a point. I like to think about it this way. You either have a point in the middle, or you have an interval that contains the point, or you have the entire number line, okay? Either a point, an interval that contains it, or the entire number line. That's the only possibilities for convergence. Now this number r, this capital R, we call it the radius of convergence. So I'll draw it out here. Let me go back to I'll do it here. So what I'm saying is when it comes to convergence, you either have a point, and that's the only place it converges, or you have some interval that contains the point. Now, you might have to include or not include the endpoints, but let's just say it's an interval. Or the third possibility would be everything. All right, does that make sense? You either have one point, an interval that contains that point, or you have the whole thing. This point right here where it converges would be the point A. Because we said we can guarantee convergence if x equals a. So it's going to converge at that point A, or it's going to be a plus some number, a minus some number. That number that we're adding or subtracting is called the radius of convergence, or it's going to be infinity to negative infinity, which would be all the numbers. Does that visually make sense? You either have a single point, an interval that contains that point, or everything.
Yeah.
Got it? Hey, for the example we did that had an interval, can y'all tell me what capital R was? Let's go, what was the one that had an interval? This one had an interval, right? This one had that interval. When we got down to this inequality right here, do you see that inequality right there? Before we split it up and started doing this, right there, doesn't that look like absolute value of x minus a less than some number, capital R? Isn't that what that looks like?
Mm-hmm.
So what would capital R be here? 1, right? 1. The radius of convergence for this is 1. We're going to do, we'll do more examples, but the radius convergence is 1. So the way, again, I like to think about it is when you think about this interval, it's all the numbers between 2 and 4, right? What's right in the middle of that? 3, right? 3, we would have had convergence for 3 no matter what, because if you plug 3 in here for x, it converges. It's going to give you zeros there. So if you look at that, this is almost like the central number. If your radius of convergence means you go out that way 1, right? And you go out this way 1. And that gives you like how wide that interval is. It's the radius of the interval, which is weird. Radius, you think circle, but it's the radius of the interval. All right, continuing. Radius of convergence and interval of convergence. For the 3 possibilities above, we have the following. So if a series only converges at a single point, what's the radius, right? What would you call the radius if it's a single point? Well, in that case, we say the radius is 0. The radius of convergence is 0. It's not, the 0 isn't where it's happening, it's how wide the interval is. And if it's a single point, it has no width. So the radius we'll say is 0. Radius of convergence is 0. Now, if the series converges for all x, that means the whole number line, we'll say the radius is infinity. And if it's an interval, right, then we actually have to find out what it is. It's some number, we'll have to figure it out. In the problem I just showed you, it was 1. But for each problem, it might be different. And the last part of this says that when you have this third case where you actually have an interval, you can have 4 different types of intervals. There's 4 different possibilities when you have an interval. You can have, did I write it? Yeah, here we go. Here are the 4 possibilities for the intervals. You either have where both sides are open or both sides are closed, or you have left side closed, right side open, or you have left side open, right side closed. Those are the only possibilities for intervals. The important thing is you'll have to check your answers. Like you have to check the endpoints if you have an interval. So in the previous examples, okay, this is a summary of what we did with the previous examples. In the very first example, we had it only converged at x equals 0, which means the radius of convergence is 0, and the interval of convergence was just that single point. For the next example we did, the radius of convergence was 1, and the interval of convergence was 2, 4, where we included the 2 and did not include the 4. And then for the last example, our radius of convergence was like infinity, because the interval was everything. I hope that that kind of lays out like the 3 different scenarios. And now we get to do some more. All right. For these 3 problems, I want us to find the radius of convergence and interval of convergence for each of these. I'm going to give you a minute or so. Let me give you a few minutes. See, basically set this thing up, run the ratio test on it, and see how far you can get with it. I'm gonna work it myself quietly, and then hopefully we can talk together about it and see if we're getting the same thing. What I'm showing there is probably not your first step, but should be like your second or third step, should look like that. Does anybody have a question on how to get to there? The thing about the ratio test in the power series is that this thing where I'm splitting up the n+1 powers into two things is it's a common theme. It happens a lot. So just kind of, just kind of get used to it. Y'all sure there aren't any questions? Okay, I'm going to keep going here. I'm going to get some cancellation. After I cancel things, I always, like I said, I put the stuff with the ends out front. And then I put the thing with X by itself. And I write down less than 1 because that's what I want. I want to know when that's less than 1. So on that square root thing, when you have the square root of n+1 over the square root of n+2, I put that into one root. And then I'm going to run my L'Hopital rule on just the inside. And when I do L'Hopital on that, I get a 1. So I'm running my limit now. That goes to 1, which means I have absolute value of x is less than 1. Are we good up to here? Any questions?
Is the -3 important?
Oh, I forgot -3. Holy shit. Okay, hold on. Yeah, it's just a little important. Thank you for pointing that out. Got ahead of myself here.
Yeah, I didn't know if you left it out because it didn't matter or something, but
no, it absolutely matters.
Okay.
Hold on. I got to go back. I saw people looking like, what the hell are you doing? Okay, so we still have -3 here, and then x, absolute value. We want that less than 1. I canceled this one, so all I had left was this. The two blue parts were my part that I'm going to put with the x, and then over here, the end stuff I put together here. So I still have absolute value over here, -3 times x. I need that less than 1. And then I let my limit go. So I get absolute value of -3x less than 1. Is that okay now? Sorry. This should be equal to absolute value of 3 times absolute value of x less than 1, which is 3 absolute value of x less than 1. And what I'm trying to get to is this. I'm trying to get to absolute value of x minus a less than r. That's what I'm trying to get to. I'm almost there. I need to divide both sides by 3. Hey, what's a? What's a?
0.
0. A is 0. Now we could have seen that from the very beginning. We had x to the n. So this is x minus a to the n. So that means a was 0 here. So do you all agree we finally have it down to the right form? I mean, this does look like this. It's x minus 0 less than 1/3. So you can now tell me what the radius of convergence is. right? R is 1/3. The instructions here were to find the radius of convergence and the interval of convergence. The interval convergence requires more work. I need to do more. I'm not done. So to get the interval of convergence, what I'm going to do is I'm going to take this, I'm going to drop the absolute value, and then create over here greater than -1/3. And now what?
We test for endpoints.
Test both endpoints. So let me test them. If X is, let's start with -1/3. If X is -1/3, let me go into the original series right here. Put it right there so I can see it. I'm going to replace X with -1/3. So I have -3 to the n, then -1/3 to the n over square root of n plus 1. Since both of these are raised to the n, I can put them together, can't I? I can multiply them. And what would that give me? -3 times -1/3?
1.
1. And 1 to the n would be?
1.
1, right? So this is what we have. And now you need to tell me whether or not that converges or diverges. So how would you go about that one?
Isn't that a p-series of 1/2?
It kind of is, except that we have the +1 under here,
Yeah.
right? If it were just square root of n, it would be p-series. But you know what, Ian? You could compare it to a p-series.
Yeah.
So maybe you run the comparison test here, right? Here's what you don't do. You don't do the ratio test. You'll never use the ratio test to test the endpoints. The reason why is because we already know that if you run the ratio test, you're going to get 1. Trust me, if you run the ratio test on this, you're going to get the limit to be 1, which means it fails. So you're going to have to use some other test. So I don't know here. Compare it. I don't know. I'll leave that to you. You compare that. I don't know. Compare it to 1 over square root of n. We should find that this diverges. It will diverge. I'm not showing the work. You would have to do that. And now we need to run the other endpoint. So if X is +1/3, we plug that into the series. And we get -3 to the n, and this time 1/3 to the n over square root of n plus 1. This time when we put those two together on top, we don't get 1, we get -1 to the n over square root of n plus 1. And how would you do that?
Alternating series?
Yep. We would do the alternating series test on that. And that would converge. Not showing the work, but that's what would happen. So now what is the interval of convergence? By the way, when I do interval of convergence, I abbreviate the interval of convergence. Let's see, did I put it up here? I didn't, but I abbreviated IC because I don't like writing interval of convergence over and over. So the interval of convergence for this series would be, so we don't want -1/3 in there, right? Because when we plugged in -1/3, we got divergence. So it would be -1/3 to 1/3, and we do want 1/3 because we get convergence there. If you don't want to write it that way, you could write it this way. Either one of those would be okay. We good? We good? We got 20 minutes. We good? Let's do another one. I'm going to move faster through this one because the next one, I want to do the last example. So I'm going to set up my ratio test. What's A? Can someone tell me what A is here? Careful.
-2.
-2. Good. It's A is -2. All right. So let's run the ratio. So I'll let y'all know how I do the ratio in my head. I do this. I have a fraction here, right? So I'm basically going to write that fraction here with n+1 plugged in. And then what I'm going to do is next to it, I'm multiply by the reciprocal of this. So let me plug in my n+1. n+1 in parentheses. And then I'm going to have the x+2 to the n+1, which means I'm going to have x+2 to the n and x+2 to the n and x+2 again. And then on the bottom, I'm plugging in n+1. So when I do that, if I do 3 to the n+1 plus 1, that's 3 to the n+2. So that means I'm going to have a 3 to the n times a 3 squared. And then on this one, it's just that flipped over, which will be 3 to the n times 3, and then n, and then x+2 to the n, like that. Cancel. I can get one of these 3's to go away. Yeah, I think that's it. So the stuff that has n in it is this and this. So I have limit, and it goes to infinity. I have n+1 over n. And then the stuff that has the x in it still is the x+2 and the 3. I won't forget the 3 this time. So I'm going to say x+2. I'm going to say 1/3 times x+2. And then absolute value. Now I need to have that less than 1. And good news here, this limit goes to 1, right? That goes to 1 when you do your n going to infinity, which means we have absolute value 1/3 times x+2, absolute value here less than 1. I'm almost where I need to be to get my radius of convergence. I just need to have that x+2 by itself. So the 1/3, I can take its absolute value, bring it out, and then finally multiply both sides by 3. At this point, I know what R is, right? R is 3. Any questions there? Why R is 3 or anything? Convert this, x+2. Now I'm going after the interval convergence. Drop the absolute value, create the string of inequalities, and now subtract 2 from everything. -5, 1. You all right with that? What next?
The endpoints.
Endpoints, check them. I got to check -5 and 1. Do it over here. If x is -5, I have to figure out what happens. If x is 1, was that what it was? -5 and 1, yeah. All right, so let's see. If x is -5, let's see what happens. N equals 0 to infinity. N times, okay, if x is -5, this turns into what? -3 to the n, right?
-3.
Yeah, -3 to the n over 3 to the n+1. Y'all good with that? I'm going to go another step here. Sum n equals 0 to infinity. I'm going to break the -1 off the 3. The reason I did that is because I realize I have a 3 to the n plus 1 on the bottom. So it'd be really nice if I had a 3 to the, 3 to the n instead of negative 3 to the n. So I just split it up. And now these two simplify, don't they? What does that turn out to be?
One-third?
Yeah, just 1/3. I mean, basically, you could look at this on the bottom as being 3 to the n times 3, and then the 3 to the n's cancel. So you just get a 3 on the bottom, right? So on the top, I have n, and then I have negative 1 to the n, and on the bottom, I have 3. All right, how are you going to tell me about that? What are you going to do here? I see it alternates. It does alternate, but what now? I didn't hear it.
But like, it's not like the ends aren't below the fraction.
Yeah, this just gets bigger and bigger, doesn't it?
Yeah.
Couldn't you just do the nth term test? The very first test we had. Remember the nth term test? It was a test for divergence. It said if you take this thing here, right? Nth term test. If you take that and you take the limit of that as n goes to infinity, so if I let this go to infinity, if it's not 0, what can we say? Diverges, right? It's not 0. That's what this very first test said. If you take the limit and you get something other than 0, it diverges. And I hope you would all agree that this limit's not going to 0, right? This number just gets bigger, and this just keeps on switching back and forth, positive, negative. And 3 is just 3, it doesn't change. So this thing is not going to 0. And so what happens? What can we say about this then? Divergence, right? Now we have to plug 1 in here. So if we plug 1 in, we get n, and then we get 3 to the n there, don't we? Over 3 to the n plus 1. See, there's no negative there this time. And so again, the same sort of cancellation is going to happen. You're going to have n over 3. And for the same reason as this one, if we run the nth term, we know that this is going to diverge. Because it's not, the limit of this is not going to 0. Which means the interval of convergence is what?
It's open on both sides.
Open on both sides, -5 to 1. Or if you like the inequality, you can just put the inequality that we had above. There we go. All right, one more. Same thing. All right, this one, I think the ratio test is gonna be a little bit tricky. Limit n goes to infinity. All right, I'm gonna take my time. N plus 1 squared x to the n plus 1 over 2 times 4 times 6 times 8 times ... all the way out to 2 times n plus 1. That's me replacing all the n's with n plus 1s. Then I'm going to multiply by the reciprocal, which is going to be 2 times 4 times 6 times 8 times ... all the way out to 2n over n squared x to the n. Which is, I get to cheat, which is equal to okay, so here's, I'm gonna just change a couple of things here. I'm gonna write that as x to the n times x. And then on the bottom here, I'm going to distribute that through. And I'm going to leave a little bit of space here. This becomes 2n plus 2 is the last one. And we talked about this in class last time. What would the one right before this one be? If the last one is 2n plus 2, what would the one right before it be? What's the pattern here? Aren't they 2 less each time?
2n minus.
It's 2n plus 2, but then take away 2, right?
2n.
So just 2n. Now it's important to see that because that's going to help you with the canceling. So let's see, let's take care of the easy ones. X to the n's gone, 2's are gone, 4's are gone, 6 gone, 8 gone, all the dot dot dots are gone. The 2n is gone, the 2n is gone. Everything else looks like it stays. All right, the stuff with n, I've got this, and I've got this, and I've got that. That stuff with x, I mean, that stuff with n's, and then the only thing I have left with x's is just the x. So this becomes limit, n goes to infinity of n plus 1 squared over n squared times 2n plus 2 times x, absolute value, we want that less than 1. Do y'all agree with that? Y'all understand that? Is there anything confusing there? I've got to figure out what's happening to this. So here's what I'm going to do. I'm going to go ahead and expand things out. I'm going to do the top. If I square the top, I get n squared plus 2n plus 1. And then on the bottom, I'm going to distribute this through. So I get 2n cubed plus 2n squared. And then times x, and I need that to be less than 1. What do you think? L'Hopital? L'Hopital on top would give us, let's just do it on the side here. If we did L'Hopital on top, we get 2n plus 2 over 6n squared plus 4n, right? We would still have infinity over infinity. So we'd run L'Hopital again. We get 2 over 12n plus 4. And where does that go?
Zero.
0. Ah, that's great. This heads to 0, which means that x, it doesn't matter what x is, right? This thing will always be less than 1. So we're not going to have an interval here. What's the radius of convergence?
Infinity.
What is it?
Infinity.
Infinity, because basically what we're saying is that you can let x be anything. So, you know, both directions forever. And that means the interval is actually all real numbers. Those are the easiest types of power series to find the interval and convergence and radius convergence of. You know, if this thing, well, not the easiest, there's three things that could happen, right? You're either going to get this to happen. If this goes to 0, then this is what happens. If this goes to infinity, then you only have one answer, and that would be when x is 0. If this goes to a number like 1 or 4 or something like that, then you're going to have an interval. So that's probably the most important part of all of these problems when you're running ratio tests is what happens to the n stuff, right? If the n stuff goes to 0, easy answer. If the n stuff goes to infinity, easy answer. It's just set that equal to 0. If it goes to some other number, well, then you have intervals. And then you have to check endpoints, and that's the more tedious problems. Okay. We made it through 8.5. So where are we on our calendar? I think we're a little behind, but let's see. No? Wow. Okay. That's good. We're on target here. How many exams have we had? 3, right? Yeah, because there was a take home. That's right. Okay. I'm like, oh crap, did we do the 3rd exam? All right, so this is good. We're in good shape, all right, because we still have 1, 2, 3, 4 class meetings. I'm guessing it's going to take us 3 class meetings to get through the next 2 sections. 3. So I'm a little ambitious here, trying to think we can get through it in 1 each, but Taylor series is going to take some time. So what I do most of the time, okay, this is normal for my Cal 2 classes, is I don't even talk about chapter 9. I normally don't even talk about it. What I do is I have my students go, I have some videos on these, and I have them watch them. Because when you get to chapter 9's, the material there is compared to everything else, it's easy. So, you know, you don't have to, we don't stress about it, all right? Because it's really, you kind of are at a point where it's like when you see chapter 9, you're like, oh, okay, yeah, that's the nice stuff. Like there's formulas, and you're not having to sit there and think through all this stuff. It's just plug and chug almost, right? So I think we're good. I have the notes for 8.6 ready to go. I was prepared today in case we got to 8.6. Where'd it go? Oh, where it just vanished. So I will send out the notes for 8.6. I'll send those out, I don't know, before we meet again. It doesn't look like there's a lot here, but there's a lot. What we're going to be doing is we're going to be taking a power series, and we're going to learn how to differentiate them and integrate them. And it's 8.6 is weird, but we're good. I'm happy. We're in good shape right now. Any questions? No? All right. I also sent out the review, right? An old review. I sent that out for a final. This was it, right? I still have maybe a minute. So this just gives you an idea of some of the questions I asked on the final, which if you look at this, it's all chapter 8. All right. So it's, write as a rational number. So I give you a repeating decimal and you have to write it. We did something like that. Find the sum. Find the sum. There's only 2 series we can find the sum of. Rewrite in sigma notation and then determine if it converges or diverges. So I give you a series and ask you to find the sigma notation for it and then determine if it converges or diverges. So you'll have to run a test there. And then look, I'm already at radius of convergence and interval of convergence, because within these problems, you will probably have to do some tests. And then from 6, 7, 8, 9, 10, 11. So 6 through 11, we still haven't talked about yet. So we still have a lot to do. All right, have a good weekend, right? I gotta go. I'll send out the notes and y'all have a good one.
Thank you.
All right, have a good one too.
Okay.